Welcome to Advanced Linear Algebra. Today, we are going to explore one of the most powerful tools in mathematics, the characteristic polynomial. Imagine you are a structural engineer testing a new bridge. You need to know the specific wind speeds that will cause the bridge to shake violently and collapse. These critical shaking frequencies are hidden deep inside the complex physics of the bridge. In linear algebra, we have a mathematical tool that acts exactly like a scanner to find these hidden critical values for any system. Let us dive in and see how it works. Now that we understand the goal, let us look at what this tool actually is. Think of the characteristic polynomial as a mathematical DNA test for a matrix. A matrix is just a grid of numbers, but geometrically it represents a transformation, like stretching or rotating space. The characteristic polynomial takes that complicated grid of numbers and boils it down to a single algebraic equation. By solving this one equation, we unlock the fundamental stretching factors of the matrix. This tells us exactly how the system behaves at its core, revealing its most essential properties. Before we see the equation, we must understand what we are looking for. In formal terms, when a matrix acts on a vector, which is like an arrow in space, it usually changes both the length and the direction of that arrow. However, there are special vectors called eigenvectors that only change length, not direction, when the matrix acts on them. The scaling factor by which these special vectors stretch or shrink is called an eigenvalue. The characteristic polynomial is simply the custom-built algebra equation whose roots are exactly these hidden eigenvalues. This brings us to the golden equation. To find these hidden stretching factors, we use the characteristic equation. Conceptually, this formula forces the matrix transformation to squash space, which only happens when its determinant is 0. Let us break down the symbols. Capital A is our original square matrix. The Greek letter lambda represents our unknown eigenvalues, which are the stretching factors we want to find. Capital I is the identity matrix, which acts like the number 1 for matrices. As the variable lambda changes, the value of the determinant changes. When we set this polynomial equal to 0 and solve for lambda, we find the exact stretching factors of our original matrix. Now that we have our formula, let us see this with a concrete example. We want to find the characteristic polynomial and the eigenvalues for a simple 2 by 2 matrix. We are given the matrix A with top row 2, 1 and bottom row 1, 2. Our goal is to construct the polynomial and find its roots. We start by using our formula. First, we construct the matrix A minus lambda I. We do this by subtracting the variable lambda from the main diagonal entries. The off-diagonal entries remain completely unchanged. This sets up our new matrix. Continuing with our setup, we now must find the determinant of this new matrix. For a 2 by 2 matrix, the determinant is the product of the main diagonal minus the product of the other diagonal. We multiply the top left and bottom right entries together, which gives us 2 minus lambda squared. Then, we subtract the product of the top right and bottom left entries, which is just 1 times 1. Next, we expand this algebraic expression using the standard expansion for a squared binomial. This gives us 4 minus 4 lambda plus lambda squared minus 1. Let us finalize this calculation. We combine the constant numbers 4 and negative 1 to simplify the expression. This gives us a final characteristic polynomial, lambda squared minus 4 lambda plus 3. Notice that the highest power is t, matching our 2 by 2 matrix size. To find the eigenvalues, we set this polynomial equal to 0 and factor the quadratic equation into two binomials, lambda minus 3 and lambda minus 1. The roots are 3 and 1. Physically, this means our matrix stretches space by a factor of 3 in one special direction and leaves space unchanged in another. Now that we have successfully used this formula, let us understand where it comes from. We are setting out to derive the characteristic equation from scratch. We start with the fundamental definition of an eigenvalue and an eigenvector. Applying the matrix A to the vector x gives the exact same result as multiplying the vector x by a single number lambda. To solve this, we need to gather all the terms on one side of the equal sign. We subtract the right side from the left side, setting it equal to the 0 vector. This is the first logical step in isolating our unknown variables. Continuing our derivation, we want to factor out the vector x. But we cannot simply subtract a number lambda from a matrix A. We must multiply lambda by the identity matrix I, which acts like the number 1 for matrices. Now we have a new matrix A minus lambda I multiplying our vector to give 0. If this new matrix were fully invertible, the only solution would be the 0 vector. But we specifically want non-zero eigenvectors. For a matrix to squash a non-zero vector down to 0, it must lose some of its dimensions. Mathematically, this happens if and only if its determinant is exactly 0. This gives us our final derived formula. Let us visualize everything we have learned so far. On the left side of the diagram, you see a two-dimensional coordinate system. The blue arrow is our special eigenvector, and the red arrow shows the matrix transformation, stretching it by a factor of lambda without changing its direction. The middle arrow represents the algebraic bridge we just derived, taking the determinant of A minus lambda times I and setting it to 0. Finally, on the right, we see the graph of the characteristic polynomial itself. The horizontal axis represents lambda, and the curve crosses this axis at two specific points. These intersection points are the roots of the polynomial, which are exactly the eigenvalues we calculated. This visual intuition leads us to an interesting question. What if a matrix does not stretch space at all? Sometimes a matrix simply rotates space. If you apply a rotation matrix to any arrow pointing in two-dimensional space, the arrow will turn, but it will not stretch or shrink. Because a pure rotation does not stretch any real vector in a straight line, we should expect something unusual to happen when we look for stretching factors. We will still follow the exact same steps to find the characteristic polynomial, but the math will reveal that our eigenvalues are complex numbers, which is the mathematical signature of a rotation. Let us see this rotation with a concrete example. We want to find the characteristic polynomial for a matrix R that rotates space by 90 degrees counterclockwise. The top row is 0, -1, and the bottom row is 1, 0. We want to see what happens to the eigenvalues. We follow the exact same steps as before. We subtract lambda from the mean diagonal, which originally contained zeros. The off-diagonal elements remain exactly the same. This sets up our matrix R minus lambda I, ready for us to take the determinant. Continuing with our rotation matrix, we now calculate the determinant by cross-multiplying. We multiply the diagonal elements together, giving lambda squared. Then we subtract the product of the off-diagonal elements, which is -1. The negative signs cancel out, giving us our characteristic polynomial, lambda squared plus 1. To find the eigenvalues, we set this polynomial equal to 0. We are looking for a number that when squared gives a negative result. This requires imaginary numbers. The eigenvalues are positive and negative I. Physically, these imaginary roots confirm that there are no real directions in space that simply stretch or shrink. Now that we have calculated these polynomials, why do we care? In the real world, the characteristic polynomial is the ultimate diagnostic tool for dynamic systems. Mechanical engineers use it to find the resonant frequencies of buildings and bridges. If the wind hits an eigenvalue, the structure could collapse. Electrical engineers use it to analyze circuits and ensure that power grids remain stable under sudden changes in demand. Quantum physicists even use it to determine the allowed energy levels of atoms, which are literally the eigenvalues of a complex matrix system. It is a life-saving mathematical tool. Let us summarize what we have learned today. The characteristic polynomial is a powerful algebraic bridge that connects a complex matrix to its fundamental properties. By calculating the determinant of the matrix minus lambda times the identity matrix, we create a custom equation. The roots of this polynomial are the eigenvalues, which dictate exactly how the system behaves, whether it stretches, vibrates, or rotates. You now understand the essential first step in unlocking the hidden geometry of any linear transformation. Great work today!